So in the previous video we have just talked about the conservation of mechanical energy. So let's just continue with some more points. So let us consider some of the definition of a conservative force. That first, a force Fx is conservative if it can be derived from a scalar quantity Vx by the relation given by equation 6.9. The three-dimensional generalization requires to use of a vector derivative which is outside the scope of this book. The work done by the conservative force depends only on the endpoints. This can be seen from the relation W is equals to Kf minus Ki is equals to Vxi minus Vxf, which depends on the endpoints. A third definition states that the work done by this force in a closed path is zero. This is once again apparent from equation 6.11 since xi is equals to xf. Thus, the principle of conservation of total mechanical energy can be stated as the total mechanical energy of a system is conserved if the force doing work on it are conservative. मतलब जो फोर्स उसके ऊपर वर्क कर रहा है अगर वो कंजर्वेटिव है तो ही मैकेनिकल एनर्जी क्या होगा, कंजर्वेटिव होगा. The above discussion can be made more concrete by considering the example of the gravitational force once again and that of the spring force in the next section. That is figure 6.1 depicts a ball of mass m being dropped from a cliff of a height h. मतलब एक हाइट पे से हम उसको फेंक रहे हैं. The total mechanical energies E0, EH and E capital H of the ball at the indicated heights 0, H and capital H are EH is equals to mg capital H, E small h is equals to mgh plus half mv square and E0 is equals to half mvf square. The constant force is a special case of a spatially dependent force Fx. Hence, the mechanical energy is conserved. Thus, EH is equals to E0 or mgh is equals to half mvf square. Vf is equals to under root 2 gh. A result that was obtained in section 3.7 for a freely falling body. Further, EH is equals to capital E small h, which implies Vh square is equals to 2gh minus h and is a familiar result from kinematics. At the height capital H, the energy is purely potential. It is partially converted to kinetic at a height h and is fully kinetic at ground level. This illustrates the conservation of mechanical energy. 6.7 is the sum where we have to find V0, the speeds of point B and C, the ratio of kinetic energies at B and C, and comment on the nature of the trajectory of the bob after it reaches at the point C. तो वो आप खुद से एक बार देख लेना. This is quite easy. There are two external forces on the bob, that is gravity and the tension in the string. The latter does no work since the displacement of the bob is always normal to the string. The potential energy of the bob is thus associated with the gravitational force only. The total mechanical energy E of the system is conserved. We take the potential energy that Ta minus mg is equals to mv0 square divided by L, where Ta is the tension in the string at A. At the highest point C, the string slackens as the tension in the string Tc becomes 0. Thus at C, E is equals to half mvc square plus 2 mgl. Mg is equals to mvc square divided by L, where Vc is the speed at C. From equation 6.13 and 6.14, we can say is equals to 5 by 2 mgl. Equating this to the energy at A, 5 by 2 mgl is equals to m by 2 Vg square, that for V0 is equals to under root 5 gl. It is clear from equation 6.14, Vc is equals to under root gl. At B, is energy is E is equals to half mvb square plus mgl. Equating this to the energy at A and employing the result from 1, namely V0 square is equals to 5 gl. Half mvb square plus mgl is equals to half mv0 square is equals to 5 by 2 mgl. Therefore, Vb is equals to under root 3 gl. The ratio of the kinetic energies at B and C is Kb upon Kc is equals to half mvb square divided by half mvc square is equals to 3 by 1. At point C, the string becomes slack and the velocity of the bob is horizontal and to the left. If the connecting string is cut at this instant, the bob will execute a projectile motion with horizontal projection akin to a rock kicked horizontally from the edge of a cliff. Otherwise, the bob will continue on its circular path and complete the revolution. The 6.7 shows a block attached to a spring and resting on a smooth horizontal surface. The other end of the spring is attached to a rigid wall. The spring is light and may be treated as massless. In an ideal spring, the spring force Fs is proportional to x, where x is the displacement of the block from the equilibrium position. The displacement could be either positive or negative. This force law for spring is called Hooke's law and is mathematically stated as Fs is equals to minus Kx. The constant K is called the spring constant. Its unit is Newton per meter. The spring is said to be stiff if K is large and soft if K is small. Suppose that we pull the block outwards as in figure 6.7b. If the extension is xm, the work done by the spring force is Ws is equals to integration 0 to xm Fs dx, that is minus 0 to xm kx dx minus kxm square divided by 2. This expression may also be obtained by considering the area of the triangle as in 6.7d. Note that the work done by the external pulling force F is positive since it overcomes the spring force. So therefore W is equals to plus kxm square divided by 2. So here are some of the values. जहाँ पे हमें फोर्स नेगेटिव मिल रहा है, एक्सिस पॉजिटिव, पॉजिटिव साइड पे हम पुल कर रहे हैं और फोर्स कहाँ लग रहा है, नेगेटिव साइड पे. हम पीछे से धक्का दे रहे हैं, मतलब डिस्टेंस कम हो रहा है और फोर्स कैसे लग रहा है, पॉजिटिव लग रहा है. ओके, इन फिगर सी, बी एंड ए. सो द सेम इज ट्रू व्हेन द स्प्रिंग इज compressed with a displacement xc. The spring force does work Ws is equals to c square divided by 2 if the block is moved from an initial displacement xi to a final displacement xf. The work done by the spring force Ws is equals to minus integration xi to xf kx dx is equals to kxi square divided by 2 minus k xf square divided by 2. Thus the work done by the spring force depends only on the endpoints. Specifically, if the block is pulled from xi and allowed to return xf, Ws is equals to integration xi to xf kx dx. So kxi square divided by 2 minus kxi square divided by 2. Therefore, the work done is 0. The work done by the spring force in a cyclic process is 0. We have explicitly demonstrated that the spring force I is position dependent only as first stated by Hooke. Second, does the work which only depends on the initial and final position. Thus, the spring force is conservative force. We define the potential energy Vx of the spring to be 0 when block and spring system is in the equilibrium position. For an extension or compression x, the above analysis suggests that Vx is equals to kx square divided by 2. You may easily verify that minus dv by dx is equals to minus kx, the spring force. If the block of mass m in figure 6.7 is extended to xm and released from rest, then its total mechanical energy at any arbitrary point x, where x lies between xm minus xm and plus xm, will be given by where we have invoked the conservation of mechanical energy. This suggests that the speed and the kinetic energy will be maximum at the equilibrium position x is equals to 0. That is half mvm square is equals to half kxm square, where vm is the maximum speed or Vm is equals to under root k upon m xm. Note that k by m has the dimensions of t minus 2 and our equation is dimensionally correct. The kinetic energy gets converted to potential energy and vice versa. However, the total mechanical energy remains constant. This is graphically is presented in this particular figure, that is parabolic plots of the potential energy V and kinetic energy K of a block attached to a spring obeying Hooke's law. The two plots are complementary, one decreasing as the other increases. The total mechanical energy K is equals to E is equals to K plus V remains constant. Here also we are having some examples. For to stimulate car accidents, auto manufacturers studied the collisions of moving cars with mounted springs of different spring constants. Consider a typical simulation with a car of mass 1000 kg moving with a speed 18 km per hour on a smooth road and colliding with a horizontally mounted spring of spring constant 6.25 into 10 raised to 3 Newton per meter. What is the maximum compression of the spring? At maximum compression, the kinetic energy of the car is converted entirely into the potential energy of the spring. The kinetic energy of the moving into 10 raised to 4 joule, where we have converted 18 km per hour to 5 meter per second. It is useful to remember that 36 km per hour is 10 meter per second. At maximum compression xm, the potential energy V of the spring is equal to the kinetic energy K of the moving car from the principle of conservation of mechanical energy. V is equals to half kxm square is equals to 1.25 into 10 raised to 4 joule. We obtain xm is equals to 2.0 meter. We note that we have idealized the situation. The spring is considered to be massless. The surface has been considered to possess negligible friction. We conclude this section by making a few remarks on conservative forces. Information on time is absent from the above discussion. In the example considered above, we can calculate the compression but not the time over which is compression occurs. A solution of Newton's second law for this system is required for temporal information. Not all forces are conservative. Frictions, for example, is a non-conservative force. The principle of conservation of energy will have to be modified in this case. This is illustrated in example 6.9. Third point, the zero of the potential energy is arbitrary. It is set according to the convenience. For the spring force we took Vx is equals to 0 at x equals to 0, that is the unstretched spring had 0 potential energy. For the constant gravitational force mg, we took V is equals to 0 on the earth's surface. In a later chapter, we shall see that for the force due to the universal law of gravitation, the zero is best defined at any infinite distance from the gravitational source. However, once the zero of potential energy is fixed, is in midstream. Consider example 6.8, taking the coefficient of friction nu to be 0.5 and calculate the maximum compression of the spring. So this one you can solve by yourself. This is the delta K is equals to Kf minus Ki, that is 0 minus half mv square. The work done by the net force is W is equals to minus half Kxm square minus nu m gxm. Equating, we have half mv square is equals to half Kxm square plus nu m gxm, where now nu mg is equals to 0.5 into 10 raised to 3 into 10 is equals to 5 into 10 raised to 3 Newton. After rearranging the above equation, we obtain the following quadratic equation. Therefore, xm is equals to minus umg plus nu square m square g square plus mkv square raised to half divided by k, where we take the positive square root. Since xm is positive, putting in numerical values, we obtain xm is equals to 1.35 meter. Okay, if the two forces on the body consist of a conservative force Fc and non-conservative force Fnc, the conservation of mechanical energy formula will have to be modified by the We theorem. Fc plus Fnc delta x is equals to delta k. Therefore delta k is equals to Fnc delta x, where E is the total mechanical energy over the path. This assumes the form Ef minus Ei is equals to Wnc, where Wnc is the total work done by the non-conservative forces over the path. Note that unlike the conservative forces, Wnc depends on the particular path I to F. Okay, so we will just stop here. In the next video we are going to start to understand various forms of energy and the law of conservation of energy. Thank you.